Today's guest, Dr. Kishore Chatterjee, Director GHRCE College of Engineering, Dr. P. She will be joining after some time. Supervisor, Dr. D.R. Tuggis, Dean R&D, Dr. Neeraj Wankhede, HOD, Dr. Prema Daigamani, faculty members and dear students, a very good morning to all of you. I, Shubhangi Punje, Associate Dean R&D, feel privileged to welcome you all to the PhD pre-submission seminar of research scholar Mr. Sayyad Naimuddin Electrical Engineering Department on topic Enhancing the Power Quality and Performance of Electrical Drives for Various Industrial Applications. Dr. Kishore Chatterjee has been with the Electrical Engineering Department of IIT Bombay since December 1998, where he is currently a professor. His research interest is in utility-friendly converter topologies, power factor correction techniques, StatCom, switch mode rectifiers, electronic ballast, control of electrical drives, power evacuation strategies from solar PV system. On behalf of GHRCE College of Engineering and R&D Cell, I welcome you, sir. And I would now request Mr. Sayyad Naimuddin to deliver the PhD pre-submission seminar.
Good morning, all of them. Respected expert, the Director of the institution, Head of the department, professors, and my dear friends. I am Sayyad Naimuddin and I am here to deliver a pre-submission seminar on enhancing the power quality and performance of electrical drives for various industrial applications. Now, I have done this work under the guidance of Dr. D.R. Tuggis, who is a supervisor with this college, and also the associate professor with Ramdev Baba College of Engineering and Management, Nagpur. Now, in my work, we have developed one energy-saving device, electrical drives, which is performing better than VFD and saving lots of energy. That's a novelty which we have done. Now, for today's seminar, the contents are the introduction, literature review, AC variable voltage drive, MATLAB simulations of the proposed work, AC to AC converter design, then experimental setups, observations and results, and conclusions. Next. You all are knowing about the electrical drives. Electrical drive is a very common thing which is required everywhere. It's an electromechanical device for converting electrical energy into mechanical energy, for imparting motions to machines and mechanisms, which is used everywhere, in industries, in commercial applications, as well as in domestic applications. Some of the applications like fans, then rolling mills, cement plants, pumps, blowers, compressors, and many others. Now, for electrical drives, we generally use electrical motors. Electrical motors are of various types, but mostly squirrel cage induction motor is preferred over other types of motors. Three-phase squirrel cage induction motors are preferred for fan, blowers, and pumps in industries. Now, for our proposed design, we have selected one three-phase induction motor, which is of 0.37 kilowatt and 0.5 horsepower. The energy which is required in almost all industry, out of that total energy requirement, almost 30 to 40% amount of energy is required for auxiliaries. These auxiliaries, they are required for cooling applications like in induced draft fans, forced draft fans, cooling towers, then other utilities, and this comprises around 30 to 40% of the total electrical energy which is required for that particular industry. Now, nowadays energy efficiency and energy saving is a key term. Now, by using energy efficient motors, we can save a lot of energy. Now, in our drive, we develop one drive mechanism which is saving a lot of energy and it gives superior performance as compared to VFD. Now, this will benefit all the industries, the country, and the whole world. Before the invention of VFDs, the topology which were used, they are phase angle control drives. In phase angle control drives, just by controlling the phase angle of power semiconductor devices, we can control the speed for which that particular drive is used. Now, these phase angle control drives, they are applicable for single phase as well as three phase converters and generally used in AC as well as DC drives. Now, three phase induction drive with phase angle control are widely used in the industry before the invention of VFD, but this phase angle drives, they are having certain drawbacks. Their power factor is very low. They give a discontinuous current conduction, and because of that a torque pulsation occurs. A low frequency harmonics which are generated, which increase losses. Now, because of this, it deteriorates motor performance as well as the input power quality. Once the input power quality of the line is deteriorated, it affects the other machineries, other auxiliaries which are connected to the same lines. Now, in order to improve this drawbacks which are under phase angle control technique, then VVF drives are deployed for motor control. VVF drives, they are the most popular drives in today's competitive market, and this variable frequency drive, which is popularly termed as AC drives, is an electronic mechanism which receives energy from a fixed frequency, fixed voltage, either single phase or three phase, and converts it into variable voltage and variable frequency, three phase for three phase drive motors. Now, this variable frequency drive output is generated using a DC ring inverter. Means first AC is converted into DC, and then this DC is again inverted into AC and is given to a motor. Now, this VFDs, they are having certain advantages as compared to phase angle drives, and that's why they are popular. And these advantages are, they are having good power factor, reduction of torque pulsation, increased efficiency at lower speed. Now, our drive which we have designed, no doubt there are further chances of improvement in each and every system. So our drive is giving much better power factor and with increased efficiency and power saving. Next, the proposed high frequency drive which we have developed, our work, it deals with variable voltage control schemes which employs only one main switch and three auxiliary high frequency PWM switches instead of using 6 switches, which is generally applicable for VFD. The scheme gives smooth starting and speed control of induction motor with high efficiency and high power factor. The developed technique is based on high frequency AC switching, which is more efficient and simple as compared to control technique which is used in VFD. And this is applicable for low performance as well as medium performance devices. This drive is not applicable for high performance devices. We are not nowhere concerned with the direct torque control, or we are not concentrating on torque of a motor. We are concentrating mainly on the variable voltage, which is sufficient to run a motor with improved power factor. Next, the objectives of our research are, the major objectives are energy saving. Energy saving is the key factor in AC drives. Then high frequency AC PWM technique with AC prevailing action for induction motor drive. A soft start and power saving for fan, pumps and blowers or related applications. High efficiency and high power factor, simple, economical and easy to control. The novelties which are included in our research is AC prevailing, controllable deadband, reduced number of switches and high frequency PWM switching for AC motors. Next, I have referred many papers, but most of the papers they are either based on phase angle control techniques or on VVF drives. So hardly some part is important for my work, but out of that some papers I have referred which are concentrating mainly on the derating factor of the motor, which is improved by their proposed technology. Next, similarly in some papers they mainly focused on symmetrical angle control, constant pulse width modulation technique. Then some people they derive their drive, instead of using conventional 6 switches they used 4 switches, which reduces the cost of the inverter and losses associated with it. Now in one paper I got some clue for our proposed work, and that's given by Ahmed and Mewade. In their topology, they presented a circuit for symmetrical PWM 3-phase AC to AC voltage controller. But even this paper is having some drawback, and the circuit which they used in their paper is supply voltage. Once the supply voltage is negative, the main switches will not conduct and IGBT will fail. AC variable voltage drive. This is the drive which we designed. The figure which I am going to show you, it shows the proposed schemes for 3-phase induction motor drive which we have developed. It consists of main power semiconductor switch S1, which is connected with the stator winding of a squirrel cage induction motor, along with a 3-phase diode rectifier, and 3 auxiliary switches S2, S3 and S4, which are connected in parallel with each stator winding of 3-phase induction motor. Right. This is the main circuit diagram where this 3-phase induction motor is having 3-phase windings. Now, this is the main switch which is connected to this 3-phase induction motor, and 3 auxiliary switches, switch S2, switch S3 and switch S4. They are connected parallel to each phase. Next slide. Now, this diagram is showing you the detailed winding diagram of the motor. Now, this 3-phase stator winding for phase A, for phase B and for phase C, which is connected to this main switch through this 3-phase diode rectifier. Now on these 3 switches, auxiliary switches S2, S3 and S4, they are connected parallel to the individual phases. Means S2 is for phase A, S3 is for phase B and S4 is for phase C. Next. Now, the principle of operation of our proposed circuit is, they are basically divided into 4 parts. One is the active operating mode, second one is the dead time mode, third one is a freewheeling mode when the current freewheels through the motor, and fourth one is the dead time mode again. Next. In active operating mode, the pulse is given to main switch S, while other switches S2, S3 and S4, they are in off condition. Means only one switch is on, and because of this switch S1 which is on, the supply is connected to the motor. Now motor receives power from the supply when switch S1 is on. When switch S1 is off, motor will not receive any power. Now in active mode, this current is flowing through the 3-phase winding of this motor depending on the direction of current, and this switch S1 will facilitate the supply to this 3-phase stator winding of an induction motor. Other switches S2, S3 and S4, they are in off condition. Now this gives a more clarity. Depending on the direction of current, let me assume that the direction of current is forward for phase A and phase B and reverse for phase C. So this current will flow through D1, then to main switch and comes back to through D2 and back to phase C. Similarly, the forward current which is flowing from phase B, it flows through diode D3, main switch S1 and comes back from D2 back to phase C. Next. Now in dead time mode, the control pulses which are designed, they are designed in such a fashion that when switch S1 is off, when switch S1 is on, during that time all the other switches, auxiliary switches, they are off. Similarly, when other switches are on, the switch S1 is off. And dead time is nothing but the time interval which is given in between these 2 pulses in order to avoid the short circuit of these 2 switches. Now this dead time, during this dead time mode, when switch S1 is off, all the other auxiliary switches like S2, S3 and S4, they are in off condition. Means all the 4 switches which are used in our proposed die, they are in off phase, and the current is freewheeling through the path provided by this RC number circuit. Now next one. This diagram is very clear. Now the current which is flowing, when switch S1 is off and all the other switches are off, the current is circulating through, means the same current which is flowing in active mode, it is circulating through this RC branch and circulated inside the internal windings of a motor. Next one. In freewheeling operating mode, the switch S1 is made off, and at the same time the switch S2, S3 and S4, they are operated. Means the switch pulse signal is given to S2, S3 and S4 and pulse is removed for S1. So current freewheels through the path provided by these freewheeling diodes along with the switch where they are connected in their respective phases. Next diagram. Now in this diagram, now looking into the direction of current, let me assume that for phase A the direction of current is forward and it is flowing from A to A dash. So this current will flow from A to A dash, then it will move to D9, then switch S2, comes back to D10 and again come back to the phase A. Now let me assume for phase C, now it's a reverse path, so it's a return path for the flow of current. So current is flowing from C to D15, D15 to S4, then comes back to D16 and comes to phase C. So in this way, freewheeling action is taking place when the switch S1 is off and all the other switches S2, S3 and S4, they are in on condition. Next. Now dead time mode 2 is the mode when switch S1 is off, similarly all the other switches S2, S3 and S4 is off. During this time, now this current is freewheeling through the RC branch which is connected to the auxiliary switches, and these are flowing from, if suppose the direction of current is from A to A dash, then it's flowing from D9, then RC branch comes back to D10 and come back to phase A. Similarly for phase C, the amount of current which is flowing in phase C, it's flowing from D15 to RC branch, then come back to D16 and come back to phase C. So that's about dead time mode 2. So here in our work there arises two dead time. One is before, once the switch S1 is, once the pulse which is given to S1 is off and switch is going to apply on the other auxiliary switches like S2, S3 and S4. In between these two pulses, a small dead time occurs. So during this time the current is flowing through the RC branch which is connected to main switch S1, and during when again pulse is given to S1 after S2, S3 and S4, during that dead time mode the current is flowing through the RC branches which are connected in the individual auxiliary, in parallel to the individual auxiliary switches. Now the operation of the proposed scheme with three-phase balance supply is analyzed in this section, with which deals with three-phase balance supply voltage, and these voltages are Vs is equal to Vm sin of omega t, Vsb is equal to Vm sin of omega t minus 120 degree. Similarly for phase C, it's Vm sin of omega t plus 120 degree. This can be written as Vsa, Vsb, Vsc, where omega and Vm are the angular frequency and peak value of phase voltage respectively. The gating time sequence for IGBT uses symmetrical PWM technique. This high frequency fixed PWM is generated by comparing a triangular wave with a DC amplitude of value Vc. Now the gating time sequence which is generated for IGBT, it uses symmetrical pulses, and these symmetrical pulses they are generated by comparing two waves. One is a triangular wave which is generated by IC555 timer circuit, and a fixed frequency, fixed DC offset which is generated by a op-amp. Now this DC offset is compared with another op-amp output with the help of a comparator, and these two signals they are compared for generating the PWM technique. The ratio of PC and VR is called the duty cycle. The duty cycle is defined as the ratio of on time of the pulse to the total time period of that pulse. The average output voltage which is varied inside the three-phase stator winding of an induction motor is controlled by the duty ratio. Now, so output voltage of the motor V0 is given as, for phase A, its duty ratio, whatever be the duty ratio multiplied by amount of potential which is applied at the input. Similarly for phase B, duty ratio multiplied by amount of input, and for phase C, the amount duty ratio multiplied by amount of input. The value of fundamental component, it can be adjusted according to the required duty cycles. Now, this duty cycle is obtained by comparing a triangular carrier waveform with DC reference signals. It's a very simple technique, which is again a novelty in our project work. As the load is inductive and switching frequency is sufficiently high, the load current are almost continuous and sinusoidal. Next. Now this is a control circuit. Here, the two PWM signals are generated. In first PWM signal is generated for main switch S1, and the other PWM switches signals they are generated for the auxiliary switches S2, S3 and S4. Now these signals which are generated, they are generated using IC555 and op-amp. Now this IC555, this is also a novelty in our circuit. A very simple technique is used here. Pin 2 is used where capacitor is connected, and in between pin 8 and 6, two resistors of almost equal value is attached. Now in between pins 7 and 6, a diode is connected. Now this is totally dependent on the charging and discharging of capacitor. The capacitor charges and capacitor discharges. Because of charging and discharging, a triangular wave is generated. Now, a reference signal, a DC reference signal is generated with the help of op-amp. Now, a differential op-amp is also used for generating a second reference signal. Now, these two signals are required for generating a controllable deadpan. Just by keeping these two reference signals as near to each other, we can control the deadpan. Means, if you want small deadpan, keep these two reference signals as near as possible. If you want more deadpan, you just vary their magnitude, the deadpan can be varied. So this simple topology is again the novelty of our project. Next. Now here, this is reference 1 signal and this is reference 2, and these are the triangular waves which are generated by IC 555 timer circuit. By keeping these two reference signals, this deadpan can be generated. Now this is a pulse for the switches like S2, S3 and S4, and these are the these two pulses, they are complementary to each other. Means when you are applying a pulse to S1, at the same time pulse to the other auxiliary switches are negative. Means they are in off state when S1 is on. And in between this, see the size of this pulse. The size of this pulse is more as compared to the size of this pulse. And in between this, a deadband is generated. This deadband can be adjusted by changing these two reference values. Now, for knowing the performance of our proposed work, we have developed a simulation. As the three-phase stator winding is not available in MATLAB, we applied RL load here, and a simulation model is developed. Using this simulation model, we got some results. Next slide. The parameters for simulation model is a maximum supply voltage is 400 volts, supply frequency 50 Hz, the switching frequency is 5 kHz, duty cycle 0.5, load resistance 18 ohm, and load inductance 26.5 millihenry. Now these are the results. These are the simulation results. This is for phase A, phase B, and phase C. These three voltages, they are displaced with respect to each other by an angle of 120 degree, and results which are obtained from the simulation model, they give a boost for doing the hardware work. Next. This is for the load current, the three-phase current which is flowing in a circuit. This is for the respective phase for phase A. Next one. MATLAB simulation of control circuit is also done for knowing about the pulses. The same technique is used here for the simulation. Next one. And these pulses are generated. This pulses is obtained in a simulation model. And after getting these results, we start developing our hardware model. So in a hardware model, we assemble this circuit. Here, 3 8-pin ICs are used and one 14-pin IC is used. 14-pin ICs are in 4 independent op-amp. Out of that, we use 3. 2 for generating reference signals, 1 is for differential comparison. Now, IC 555 is used for generation of triangular waves, and reference voltage 1, reference voltage 2 is compared with that of triangular wave for generating the pulses for main switch S1 and the pulses for the auxiliary switches S2, S3 and S4. This knob is used as, this is basically used for changing the duty ratio. Depending on the duty ratio, the speed of the induction motor is varying. Next. The components which we used in our project, IC7812 is used for 12 volt supply, IC7912 is used for minus 12 volt supply. Now LM324 is a comparator IC, it's a high frequency IC. IC555 is for the generation of triangular wave, it's a carrier frequency generator. LF356 is used to compare the two waves. One is the triangular wave and second one is the DC offset. LF356 again a high frequency IC. Now the resistors which are used, they are 1 kilo ohm and 10 kilo ohm. The capacitors used for developing control circuits, they are 470 microfarads, 10 microfarads, 0.01 microfarads, 0.02 microfarads and 0.1 microfarads. For dividing the potential for the different ICs, the potentiometer is used of 10K and 1K. This is the actual hardware which we have developed. Here, This hardware is showing you mainly the 4 switches. This is the main switch. This main switch where these 6 fast recovery diodes are used. Now, depending on the signal of S1, when signal is given to S1, the motor will receive power. When signal is not given, the motor will not get any power. Means it is totally dependent on the signal of switch S1, whether the power is supplied to the motor or no. Now, when switch S1 is off, after a short dead band, the pulses are given to switch S2, S3 and S4. These pulses are given simultaneously. Means when switch S2 is on, at the same time switch S3 is on, similarly switch S4 is on. This is a control circuit. The complete hardware which we have developed. So here a 3-phase power is given to the motor with the help of 3-phase thermostat, a hardware module, then a 3-phase induction motor. The motor which we used for our work is of 0.5 horsepower, 0.37 kilowatt. A power factor meter is used in order to know about the readings, how the hardware is performing. Similarly, other meters are used like ammeter, voltmeter and oscilloscopes for knowing the results of voltage, current and comparing their respective phase voltage and phase currents. Next. Now, for designing a power circuit, we have used the components IGBT. The model name is KGT25N120 NDA. TLP for optical isolation between the pulses. Ultra fast diodes for faster recovery. Then rectifier diodes. The diodes which are used for main switches of 6 amperes and the diodes which are used for auxiliary switches, they are of 3 amperes. The snubber resistance and snubber capacitance of 0.01 microfarad and 100 ohm. Resistance of 1 kilo ohm. The rating of our motor is 220 volt. The input power is 0.37 kilowatt. It's of 0.5 horsepower 3-phase induction motor. The rated current is 1.8 ampere and supply frequency is 50 hertz. Now, the switching frequencies. We use 2 frequencies. One is at 2 kilohertz, 9 to 9 input voltage is 100 volt and dead time is of 5 microseconds is maintained. Using duty ratio 0.27, these 2 pulses are obtained. One is for the main switch S1 and these pulses are for the auxiliary switches S2, S3 and S4. For these pulses, we obtain this much amount of potential, this much amount of 3-phase voltage along with the current. And just by looking into the voltages and current at the output of a motor, we can say that the current is almost in phase with the amount of potential which is applied to the 3-phase stator winding of an induction motor. Next. 0.925 power factor is obtained at a speed of 1042 and the power consumption is also very low. It's hardly 41.72 watt. This is giving the 3-phase input voltage for R phase and input current at a duty ratio of 0.27. Similarly, for duty ratio 0.54, this much amount of pulses are obtained, which is applied to the respective switches, which S1, S2, S3 and S4. For this much amount of potential is obtained. Even this potential, the current which is flowing in the 3-phase motor, it's almost in line with the amount of potential which is applied at the input of the motor. Now, just by looking into this, one can say that the amount of current which is flowing inside a motor, it's almost in phase with the amount of potential which is applied at the respective 3 phases. So power factor is improved. Next one. 0.915 power factor is obtained at a duty ratio of 0.54 with a speed of 1188 rpm and the power consumption is as low as 38 watt. Next. This is for the respective R phase, the amount of current which is flowing in the R phase winding of a 3-phase induction motor and the these are the three-phase voltages which is applied on a motor. Now, for knowing the performance of our drive, we have compared our result with that of VVF drive, variable voltage, variable frequency, or VFD drive. Now, we compared the R phase voltage and current with the same R phase voltage and current for a VFD drive. Just by looking to this waveform, see the amount of current and the potential which is applicable for our proposed drive, and the amount of potential and the amount of current which is flowing using VFD. Just by looking to the diagram, one can say that this is superior as compared to this one. And this reading is noted at a speed of 1188 rpm. Our drive has given a power factor of 0.915 lakh, whereas a VVF drive at 1188 speed gives a power factor of 0.422. This diagram itself concludes that the power factor is improved. Next. Similarly, for source voltage and source current, without filters, we compared the results with that of VFD and proposed drive at a speed of 1294 rpm. The power factor obtained from our drive is 0.9, and for the VFD at a speed of 1380, the power factor is 0.472. And this is about the amount of potential which is available at one phase of three-phase induction motor and the amount of current flowing through the same phase. This is the waveform of three-phase induction motor, three-phase motor voltage and load current with input filter at a duty ratio of 0.8. Means almost full voltage is applied. Next. Now, the readings which we obtained, we compared these readings. We have noted down these readings. Similarly, we have plotted the graphs. The input power factor, we have taken care, especially for input power factor and input power, which is applicable for both the drives, for VVF drives as well as for our proposed drives. So at a speed of 1310, the VVF drive gives 0.43 power factor, whereas our drive is giving 0.92 power factor. Similarly, about the power consumption, VVF drive is consuming 60 watt, whereas our drive is consuming 41.5 watt. Now, as you go on increasing the amount of speed, no doubt, even for our drive, the power factor starts deteriorating. Means, especially at lower speed, we are getting really good power factor, which is a highly appreciating thing, because especially for fan blowers and compressors, which is used for long duty hours, and especially in induced draft fans and forced draft fans or for cooling purposes, where the fan is running for almost continuous duty, this speed will improve the power quality. Similarly, it saves your energy, which affects in the bills of industry. The expenditure, the operating expenses of industry is minimized if suppose they are using a proposed drive as compared to the VFD. Next. Now these two curves, they are plotted, speed versus input power factor for a proposed drive as well as for VVF drive. Just by looking into this curve, we achieved almost a 50% saving. Input power which is taken by VFD, for slower speed which is like this, it's varying from say 60 to almost 190 or 185 watt, whereas for our drive it's varying from 40 watt to maximum 80 watt. So at this speed, if suppose it's 1426 rpm, at this 1426 rpm, if I am comparing the amount of if I am comparing at this speed, 1442, the amount of power which is consumed is 183.1, whereas for our drive it's 74.52. It's almost saving of 60%. So it reduces the energy bills for industry. Similarly, for commercial applications, if it is used. Next. Similarly, we have drawn a curve for input power factor versus speed for both the drives, for VVF drives and proposed drives. So for proposed drives, the curve is this one, which is showing the improvement of power factor at each and every speed which we have noted for VVF drives. Now, for VVF drives, the power factor is in the range of say 0.4 to 0.5, whereas for our drives, the power factor is varying from 0.5 to almost 0.9, which is a huge improvement. Next one. Similarly, we have noted the readings of input current and motor current for both the drives, and we have compared these readings. For input supply current, our proposed drive is absorbing a current of say 0.9 ampere, whereas the VVF drive is absorbing a current of 1.44 ampere at a speed of 1310. Similarly, if you are increasing the amount of speed, at the top speed, the amount of current which is required for VF drive is 1.812, whereas for the proposed drive, it's almost same. But at lower speed, see the reduction in the amount of current, and because of this reduction in the current, the power or energy can be saved. Similarly, the motor current, now see VVF drive is absorbing somewhere around 1.2 ampere current, whereas our proposed drive is taking only 0.725 ampere. And as you go on increasing the speed, no doubt the amount of current absorbed or current taken by the motor go on increasing, and at top speed it's almost equivalent to that of VFD. Next. We have drawn a chart for speed versus input current for both the drives. Our proposed drive curve is lying below the chart of VVF drive, which simply concluding that the amount of current taken by the proposed drive is lower than the amount of current taken by VVF drive. Next. Similarly, we have drawn a speed versus motor current chart for VVF drive and proposed drive. In this chart also, our proposed drive chart is lying below the chart of below the graph of VVF drive. At only this speed, it's somehow near. Next. Now, similarly, we have noted the readings for the amount of temperature rise for the motor. Now, the temperature rise of motor using both drives, using VVF drives and using proposed drives, after 10 minutes, 20 minutes, 30 minutes, and these readings has been taken up to 80 minutes. So for 10 minutes, after 10 minutes time span, the VVF drive temperature is somehow 10 degrees centigrade, whereas for our proposed drive it's also the same. But after some time, means after an hour, for VVF drives it's somewhere around 64 degrees centigrade, whereas for our drive, the temperature rise of the motor is hardly 35 degrees centigrade. And why this is possible? This is possible because of the less consumption of current. If our drive is consuming less current, no doubt the temperature rise as well as the amount of process which are taking place inside the three-phase stator winding of the induction motor is somehow less as compared to that of VVF drive. Next. We have drawn a chart for time versus temperature, and again in this time versus temperature chart waveform, the proposed drive chart is lying below the chart of VVF drive. Next. See, we have noted this is the video of our proposed drive. The amount of potential which the drive is taking. The power factor at which the motor is running. .867 with a power consumption of hardly 23.79 watt. With a current of 0.467 ampere. This is a motor on which this fan load is applied. These are the three-phase stator voltages. Power is as low as 26 watt and current is 0.467 ampere. Power factor 0.86. Current is as low as 0.4 ampere or 0.5 ampere max to max. With improved power factor and lot of power saving. The same motor is run with the help of a VDF drive. See the amount of power which is consumed by the motor. This is a VDF drive. The amount of current in our proposed drive is somewhere around 0.4, 0.5. Now for this it's somewhere around 0.8, 0.9, which is almost double. This is the same motor. Next, start with curves. Next. So we can conclude from these comparisons of our proposed drive with that of VFD. We require reduced number of switches and hence less maintenance. Similarly, the cost, initial cost which is required for the purchase of any drive is very economical in case of our drive, whereas it's very costly for VFD. It's a high power, high converter efficiency. It gives high converter efficiency with high power factor. Power saving and efficient control is possible with our drive. It's the control technique which is used is very simple. Whereas in case of VFD, the control strategies which is used is very complicated. Now temperature of the motor is not increasing, which is additional advantage of our proposed drive, which has not been possible with that of VVF drive. Now applications, it can be used everywhere in each and every industry, and this proposed drive is especially for those applications where very high or precise performance is not required. This drive is not applicable for servo applications. This drive is not applicable where variation of torque is required. This drive is not applicable where abrupt braking and abrupt switching is required. Now this is next one. We have shown this drive to mainly 3-4 companies. Out of that, 2 companies has recommended our work. One is Escape from Pune. Second one is Bharat Polymer from Aurangabad. Now we have submitted a paper on AC freewheel PWM controlled 3-phase induction motor drive using single main switch and 3 auxiliary switches, and we are waiting for the review of this paper. Next one. I have published mainly 7 papers. Out of that, 5 are in international journals. 1 is in international conference and 1 is in national conference. Next one. These are the references which I have referred. Thank you. Any questions? Sir, even demonstration is available in our slide.
So, can you go to the first slide?
Yeah, yes. Slide number.
Slide number 2, rather.
2.
Second, sir. Next. Next. So, what do you mean by phase angle control drives?
Phase angles are where we can adjust the firing angle of a switch or semiconductor switch, and we can control the speed with which the drive motor is running.
So, you are talking about AC voltage control.
AC voltage. I'm focusing totally on AC voltage.
Okay. Now, in AC voltage control, what parameter you are changing to control the speed?
Voltage, frequency.
In AC voltage controller, which parameter? Okay, fine. Let me ask a very basic question. In order to control the speed of an induction motor, which parameters you can change?
NS is equal to 120 F by P. So we can change the speed either by changing the pole or by changing the frequency.
Pole is ruled out.
Pole is out.
So, which parameter to change to vary speed?
Mainly the voltage.
Voltage?
Yeah.
Only voltage?
Voltage.
In this AC voltage controller,
Yes.
you are changing the pole. You are not changing the frequency.
No. It's a fixed frequency and variable voltage.
What is the problem with this fixed frequency variable voltage control drives?
Sir, there is no problem, but there is always a chance for improvement. Nowadays, VFDs, they are very popular and they are having really a superior performance as compared to phase angle drive. But the drive which we have developed, it's giving again superior performance because of AC freewheeling. Sir, there is a stage, a DC stage in between.
No, we'll come to VVFD later. So here you are actually trying to improve upon your phase angle control drives, or what you mean by stator voltage control.
Yes.
Right? So you are controlling the voltage of the stator.
Yeah.
Now, if you control the voltage of the stator to control the speed, right? So why speed is actually changing as you are reducing the voltage? Which parameter is increasing?
By changing voltage.
If you reduce the voltage, why speed is actually reducing? Okay, there is no board. That is behind us. You can just What is actually increasing? So these are, as you are reducing the voltage is going on. So that means as if you for a given torque, what is actually increasing? Why speed is falling as you are reducing the voltage?
Torque is
Torque is given torque, so that is constant. So what is actually reducing?
torque is reducing.
Torque is the load torque. Right? The machine has to develop the same load torque. So what is actually increasing or reducing? So that the speed is falling. Like something has to happen. No? As we are reducing the voltage, we are not changing the synchronous speed. Frequency is fixed. So something has to change, no, in order to reduce the speed. So what is actually changing? What happens to sleep?
Yeah. Sleep is basically it's a difference between NS and
What happens to sleep if you are reducing the voltage?
sleep reduces.
Sleep reduces. So if sleep reduces, then the speed will increase.
Sleep increases.
Sleep. If sleep increases, what happens? So far as the efficiency is concerned, if sleep increases, what happens to the efficiency?
Rotor speed reduces.
No, I'm talking about efficiency.
Sleep
If
increases.
you operate the same drive at a higher sleep, what happens to the efficiency of the drive?
Decreases.
Why?
Because sleep increases. Losses increases.
Which loss?
Mainly the copper loss.
Rotor.
Rotor copper.
So now the thing is that in this case, in phase angle control drives, which we are actually modifying, they are also reducing the voltage, effective voltage applied to the machine, while you are keeping the frequency same. So effectively you are increasing the speed to reduce the speed. So if you are increasing the speed, so that means the rotor copper loss keeps on increasing. So how is efficiency improved? Because one of the commentaries are highlighting point is that you are getting a better efficiency compared to PVA. Right?
Basically, sir, the power factor.
Forget about it. We'll come to power factor later.
Yeah.
But definitely your drive is operating at a higher value of sleep. So if it is operating at a higher value of sleep, therefore the rotor copper loss has to be higher than that of a drive which is operating at a lower speed. Right? Go to the next slide. Let's come to this later. Next. Where your basic circuit diagram is here.
Next one.
Circuit diagram. Right. Previous. No, next. Previous. So effectively what you are doing is that you have opened the start point of the windings and then you have connected that directly. So when the switch S1 is on, so you are applying the voltage. When the switch S1 is off, you are decoupling the induction motor from the supply. So basically it is an on and off control.
Yes.
And by controlling the degradation of the on and off, you are applying a variable voltage, stated voltage to the machine. So therefore, the effect or the performance which is all the stated voltage control drive should appear over here. Right? And what are the limitations of stated voltage control? One problem I have mentioned, that as you are reducing the speed, your sleep increases and therefore the efficiency falls. What are the other problems of stated voltage control? That as you are reducing the voltage, what happens? The flux reduces. Air flux reduces. So what is the repercussion of reduction in air flux?
No doubt, the rotor speed will decrease. Rotor EMF will
For a
decrease.
given torque.
Torque will reduce.
No. See, if you are applying a load torque on the machine and the machine is operating, so that means by Newton's second law, the machine is developing the same load torque, same torque what the load is applying on the machine. Right? So for a given torque, if you are reducing the voltage, keeping the frequency same, what is the repercussion of the flux?
Flux will reduce.
Flux will reduce. So what is the repercussion of reduction in flux?
Flux cutting action will reduce and the amount of EMF which is developed in the rotor, it reduces. So ultimately torque reduces.
No, torque can reduce, no, Newton's second law.
Okay, okay.
The load,
Power factor will.
if flux reduces, power factor will reduce. What happens if flux reduces? For a given torque, if the flux reduces, what is the more important thing that happens? What is the expression for torque? Roughly, what is the expression for torque?
It's E2 I2 cos factor. It's S E2 square R2 upon R2 square plus
No, that is a steady state torque. So basically, the fundamental torque expression deals with which parameter? For any electrical machine, torque is
flux and vacuum. Yeah.
So if for a given torque, if the flux reduces, what happens to the current?
Rotor current or stator?
Whatever. If the rotor current is reducing or decreasing, what happens to the current?
If flux is reducing, current will
So that is the other problem of stator voltage.
losses. Copper losses.
Constant target. But this is not constant target.
Alright. No, but he is comparing with the same load. Because he is using that.
Only fan load.
Sir, I told you that this drive is specifically.
You are comparing both with the same load.
But almost torque is almost same. It's constant torque.
Which one is constant? No, as you are getting the speed.
Yes.
See, when you are comparing this with your VDA.
Speed variation is very narrow, sir. It's not for a wide range.
So the speed variation in
A
this
small
case.
reduction in torque it hardly affects the performance of fan motor.
No, so speed variation in case of this VDA, in your case, and the speed variation in case of your this stator voltage control case, both the case you are keeping the same.
Yes.
So the load you are exactly keeping the same.
Yeah.
But you are getting a current which is higher, lower, white. It can't be. If your flux is reducing, or a reduction is, if the torque is same, if the torque varies, is fine.
Sir, torque slightly reduces, but it hardly affects the performance.
No, torque, because you are using the same load, same fan load, with the same speed. So the torque, load torque has to remain the same. Are you getting the point? See, if in one case you are applying constant torque, in the other case you are applying fan load, it's fine. But in both the cases you are using the same load. You are using the same, if you have, I understand that you have used the same variation in speed. So therefore the torque, load torque in both the cases has to be same. So if the load torque has to be, in both the cases are same, so therefore the machine torque, the machine is developing, at the same speed has to be same. So you are developing in both the cases same torque, but in one case with the rated flux and in the other case with the reduced flux. So in your case you are definitely as you are applying lower voltage for the same frequency. So your flux is reduced, lower flux, and you are servicing the same load torque in both the cases. So therefore the current, as per the principle, the current has to be more in the case. But you are showing the current less. This has to be substantiated. You have to do a proper analysis or proper justification to substantiate. Second thing is that, see, why you require those free-wheeling diodes, those circuits. Suppose say, the switch S1 is on, right? The current is going through the winding through the diode, some of the two phases of the diode, and ultimately it is getting shorted. So ultimately you are connecting the motor to the source. Now when you are turning off the switch S1, right, what is going to happen?
So the amount of energy which is stored in the windings.
So if I don't have those three circuits, what is going to happen?
When switch S1 is off
Off.
and before switching S2?
No. Suppose take a hypothetical case that those three circuits are not there.
Okay.
Let us remove those circuits.
Free-wheeling.
And only this S1, the circuit with S1 is there. Now, if I turn off the switch S1, what is going to happen?
So the amount of energy which is contained in the inductor, it has to be dissipated. So it will dissipate it as a heat.
Where?
In the winding itself. Or it will not allow switch S1 to move from on state to off state.
No, you have turned off switch S1. It The self-commutated.
So it will get circulated inside this.
Where?
This.
See, we have turned off the switches one.
Yes.
What is going to happen to the current flowing already? Because it is an inductive circuit, inductive path is there. Right? Current is flowing through an inductor. So you have broken the current. So what is going to happen?
Current will be zero.
Is zero? Immediately it will come down to zero. Can that happen?
Yeah. Yes.
So what is it? So the current will still flow through one of these diodes, two of these diodes, and charge this your RC circuit. So now my question is that why you have put these three circuits?
Sir, whatever the amount of stored energy which is contained in the winding, it has to be circulated. And
You know, it's not circulated. You are passing that. Suppose say in your case, what you are doing is that when you are turning off the switch S1, you are turning S2, S3, and S4 off. Means that when this switch is being turned off, the magnetic energy stored in these leakage inductance of these windings, they get shunted. They turns on those diodes, right, of these three circuits, auxiliary circuits, and it goes to that other circuit. And in the normal practice, you are keeping switch S2, S3, and S4 on. Now, in the normal case, you are keeping the switches S2, S3, and S4 on. So,
when switch S1 is on, all the other switches they are off.
okay,
They are off.
and when S1 is off,
When S1 is off, a small dead time is given, and after that dead time, this switches S2, S3, and S4 they are made on.
so that means you are trying to transfer the stored energy, magnetic energy, of the leakage inductance to that circuit. Why you want to do that? This can be done in this circuit itself. When you are turning off the switch S1, right? You are giving a dead zone. So that means there is a time event when none of the switches are on. Nothing is happening to the switches. So that means during that time the energy is being transferred to this RNC. So if you continue with this, what will be the problem? Continue with that. Continue means that you don't have these other three auxiliary circuits. So what I am trying to understand is that what is the benefit of employing those three circuits along with three switches?
High interference.
Right? If you break an inductive current, what happens? The LDI by dt drop becomes very large in the reverse direction, and it will turn on the diode. Whatever will the voltage of the capacitor, one of the diodes will be turned on.
And they get circulated inside that
Not
winding.
circulated. This gets charged. The energy will get down to that capacitor.
This circuit. So because of that heat develop inside the stator winding of the capacitor.
No. What I'm saying is that instead of distributing that energy into these four circuits, why not transfer it to one circuit? Or what is in your mind to distribute that magnetic energy into these four circuits instead of one circuit?
For high power application, what will happen? Whether that capacity will be sufficient to store that energy.
No, that is not sufficient.
For that you are using it.
So after
Sir, for low power application it's possible, okay. Even if suppose these three switches are not used, whatever the amount of energy which is contained or whatever the amount of energy which is contained in the capacitor, that is circulated. But for high power applications, for higher rating motors,
what do you mean by circulated? That energy is there in the capacitor, and that energy you can't do anything, right? Because the current
in that case the size of the capacitor will
no,
increase.
we'll come to the side. See what we are doing with that energy that you are trapping from the magnetic circuit of the phase windings of the machine. You are dumping it on the capacitor. After that, what you are doing?
After that all the three switches, auxiliary switches, they are on. They are circulated inside.
Circulated means because current cannot flow in the left hand side.
In the winding itself. In the
Windings. No, the energy that you are dumping on the capacitor, that energy where it can go,
Will again use when S1 is again on.
where it will go.
It will be used inside the windings.
How can it? Current cannot flow through the diode in the reverse
It
direction.
will be dissipated.
Where it will get dissipated?
So resistance, number resistance.
Right. So, and what happens to the other two circuits? They are coming with also resistances that you have not shown.
Yeah, yeah.
Right.
Actually, this is.
So all the energy that you are trapping, you are actually wasting it in another form.
But that number circuit is required in order to avoid high dB by dt.
No, what I am asking is that see, you are putting three such circuits. Instead of that one circuit with a higher value of capacitor, you are using three capacitors now. These three diode bridges, external diode bridges, right? Three extra resistors, three extra capacitors. Instead of that, you could have designed a proper value of capacitance. Next is that you are wasting that energy. Right? Because ultimately you are dissipating that thing in that resistance. That is so
Very small duration.
That is very small, the order of some microseconds.
Then the next question is that how you are improving the efficiency. You know, stator voltage control, right? This freewheeling circuit is not helping you out in improving the efficiency because the power that magnetic and stored energy that you are getting, that you are actually wasting. So basically, it turns out to be a stator voltage control. So how you are claiming that your efficiency is good? Because the thing is that you are demonstrating, but then you have to substantiate the analysis and proper justification.
That analysis part is not very
That analysis part is missing. Right? Because when you are presenting a case, it has to be supported first by your analysis. Right? Then it has to be supported by your simulation and then it's done. So if the analysis part is missing, then people will keep on asking this question.
The freewheeling portion is for longer time and that capacitor is charging for very small time. That is the main reason why the circulation is held in the presubmission answer. Duration, the फर्क है ना, freewheeling duration is longer and red band is very small.
very small.
No, because what you have to substantiate is that basically it is a stator voltage control, right? Where you are actually not stator voltage control, you are actually, it is more stringent, you are doing on and off control. Right? You are supplying the AC voltage for certain duration and you are supplying zero voltage for certain duration. So it is more detrimental from the point of view in that.
But conduction is continuous, the amount of power consumption by the motor is
That's
very
what I am
less.
questioning. How? So you have to
See,
show
current is not discontinuing anywhere. But
current can be-
even if people are
you
providing
can't have
pulses,
discontinuous current to a magnetic field. You are providing a path by this input low pass filter. Right? If you remove the filter, current will become discontinuous. The whole thing will get burned. The filter over there is making the current continuous. But ultimately, you are switching on the fan for some duration and switching off the fan for some duration. What you are using for your air conditioners on off control. But it has got the same problem, right? Because it's nothing but a stator voltage control, right? Even worse than that.
but for industry, sir, the fan is running almost continuous
So
throughout
that's
the
why-
day and night.
So that's why in industry they use this, what you call the phase angle control or stator voltage control for fan drives. Now you are saying that you are improving upon that. So that substantiation has to be there through analysis before you show it to other results. And actually you have done it at a very low power level. The experiments that you have carried out is 1.8 amps. So magnetizing current itself is of the order of 0.8 amps. 0.8 amps, 1 amp, even more. So what current you are actually measuring, you don't know. Are you getting what I am saying?
Yeah.
Because the current levels are 1.8, whether it is the magnetizing current or the rotor current, you never know. So that's why there is you can't compare at that power, low power level. So that's why your experimental results are showing that much phenomenal improvement. But if you see the analysis, it can't be. Because essentially it's a stated voltage. So you have to ensure that through analysis, or you have to sell it from a different, you have to give a different color to it.
Maybe we have reduced torque and speed both.
No, so that anyway he is reducing in case of VVFD also. Now coming to the power factor, see you are comparing the power factor of this with your VVFD. Now go to that current, the two pulses of current that you have shown in case of VVFD. That current is actually the current of the input current of a diode wave.
Table.
No, no. Go ahead, go ahead. Go ahead. Go ahead, go ahead. Go ahead. Alright, previous. See this current on the right hand side, these two pulses, this is actually the input current of a diode wave, three-phase diode.
This is from DFD and this is from.
So you can't compare these two. Because the VFDs which are there in the market, they can't sell the VFD with these currents. They have an active power filter in front of their drive. Right? So this comparison actually is not valid. Are you getting what I'm saying? See, in a VFD you have a diode bridge to convert AC to DC, and then you have the inverter. And you are comparing that input current, which is the input current of the diode bridge. So the thing is that if you see that the proper VFDs which are available in the market, their input current will not be like this. They will be using an active power filter or passive filter and ensure that that current is sinusoidal current. The power factor improvement that you are actually projecting actually is due to that. The VFD what you have used is they have maybe an experimental one, so they are using only a diode and then filter diode. So now you have to compare apples with apples, right? Because your power factor, on what aspect the power factor depends? Yes, you have to compare your phase angle control right with your this. You take a phase angle control, not VFD. You have to take a phase angle control right, where you are controlling the firing angle of the AC voltage controller. Show that what power factor it is operating, and then you show your power factor, not with VFD. Because ultimately your drive cannot be compared with VFDs, because VFDs they are maintaining constant flux in the air gap. In your drive you are not maintaining constant flux, right? So you have to compare your drive with the stator voltage control or the phase angle control drive.
But in little states, sir, for most of applications like fan, pumps, they use same VFD, which is available in the market.
So that is why they are doing that. That should not be done. Right, for things.
So my main focus is to save energy. See, for small applications, if we are using such a
save energy, you can say that okay, fine, don't use VFD, use stator voltage. But why this drive? When you are saying that your drive should be used, then you have to compare this one with your stator with the conventional stator voltage control drive or this phase angle. Then that comparison makes sense. Because in your case, flux is not constant, flux is reducing, power factor is, this your, not torque remains same. For a given torque, a low torque, the machine has to develop the same torque, otherwise it will rotate. So the thing is that your stator rotor copper loss is increasing. The efficiency definitely is less than your VVFD. Where VVFD sleep is always maintained constant for all speeds. Whereas here your sleep, you are controlling the speed by increasing the sleep. So definitely your efficiency will be poor compared to VVFD. Right, so all these things have to be substantiated in a proper analytical. You should have a proper analytical basis. Then the simulation, then the experiments will come. And also this, while performing the experiment, be careful. You have performed at a very low power level, where the current levels what you have chosen is much lower than the magnetizing current of the machine. So whether it is the load component of the current or the magnetizing component of the current, you never know. Probably what is happening is that as you are reducing the voltage, your the magnetizing component of the current is reducing. In your case, right? You are reducing the voltage, so Xn, you are applying lower voltage across Xn, so your the magnetism IN is reducing. So you are getting a current which is getting reduced. Whereas in VFDs, they are ensuring the rated current, rated magnetizing current flow. So therefore, whatever may be the speed, they are ensuring that V by A being constant, so the magnetizing current which is flowing to the Xn, the parallel band, remains constant. So therefore, as you are reducing speed, in your case, you are getting a reduction in magnetizing current. Whereas in that case, there is no reduction. So you can't compare these two at low power level. So you have to compare, put a proper power level, power at top in both the cases. And then compare. Are you getting what I'm saying?
Yeah.
Right? Magnetizing current in your case is reducing, that's why your current, you are getting a lower current. But in VVFDs, they can't reduce the magnetizing current. So if at all you have to compare, you cannot compare with VVFDs, but you have to compare with stator voltage controller, the conventional stator voltage. Right? So a little bit more analysis is required.
For lower and fan applications, that reduction in magnetizing current is
It's not detrimental. So therefore, you should compare.
it is a specific applications for lowers because
We are not doing it for.
No. So if you say that, then the buyer will say, oh, why? Okay, fine. That is
Sir,
the case.
actually, we have developed a work for fan, pumps, and compressor kinds of job.
If you come to me
This
to
model is
sell,
not applicable where.
no, I am not talking. If you come to me to sell your product for fans and pumps,
Yeah.
right? So you say that don't use VVFDs. I will say I agree. Then I will ask you that why your scheme and not the stator voltage control. Right? It is agreed. VVFD I will not definitely use. But then I will ask you that why your scheme and not the conventional stator voltage control. So you have to now answer, give me those solid data that your scheme is better than the stator voltage control. Right? Agreed. VVFD I am not going to use.
So even in this case also, the proposed rate is better than phase angle control rate.
So that's what I'm saying. That you have to keep that result.
Power factor when
Power factor.
Power factor is improved.
So, no.
Losses are
Right, so
minimized.
that's what I'm saying. Don't compare with VPF. Compare with the regular stator
that will be
voltage.
simple.
That's much simpler, sir.
Yeah.
Because we want to show that it's better than VFD. If suppose we are comparing with our
you
phase
can't do
angle
that
control,
because see,
then it's very easy.
VPFs are not meant for these fans and compressor type of drives.
But they are being used.
Sir, but they are used in each and every industry, everywhere.
That is different. No, but
Even they are used for
I'm observing in Mahindra and Mahindra, I'm observing at Indira Vasant, even at SKF, sir. Everywhere they apply VFD.
that is there, but
For exhaust fan.
from the
For
academic
industrial
point-
sheds, they are using exhaust fan, they are using VFD. What is it?
From the academic point of view, when you are comparing something, you have to exert the same kind of loading in both the cases.
Then that is definitely true that it is not giving a
Yeah, so-
constant V by F, that is not there.
And even in our experimental
But that is not
work, we
required.
run the motor with our proposed ray and we run that
Because it
same
is
motor.
not
with
required.
VFD. And then we compare the things. And based on that comparison, I arrived at this conclusion.
This is not suitable for constant torque drive. This is suitable for fan.
So that's why. So that's the thing is that you compare it with your stator voltage control, right? If you want to retain it, this VPF is fine, but the comfortable stator voltage control is more. Second
Sir,
thing is.
applications of VFDs are tremendous.
No,
VFDs are
I'm
used everywhere.
I'm not talking about VFDs. The compressor. Second thing is that you are using a filter. If you use the same filter for the stator voltage control, right? Then what is the power factor improvement in your case?
So, but in case of phase angle control, the firing angle itself deteriorates the power quality. Because you are firing, either you fire it at 5 degree, 10 degree, it means you are lagging the current
that's
right
right.
from beginning.
So that has to be the compared. That in case of phase angle control, right, as the
कोई additional आप कर लेना.
that as the angle is increasing, so power factor reduces, and then you use the same filter. You can't change the filter. With the same filter, what improvement you are getting. Right? And then another important issue is the torque pulsation. In phase angle control, right, that you are applying the voltage, the stator voltage at least for quite some time. Whereas here you are turning on and off. So the torque pulsations usually come up voltage. So you have to estimate the torque estimation, if not measure.
Here it will be less because there is no discontinuous in current.
There is no discontinuity in the current means that
Current is continuously flowing.
In stator, current is continuous, but it is not drawing continuous current from supply. But current is continuous.
Right. So you point hydrate those points rather than these components. Because moment you present is
Actually, I am comparing with VFD. That
you can't compare.
Actually, I am comparing.
You are comparing with the direct bridge. You can't do that.
Because there is a divergence in
But
VFD.
how we can observe
Divergence in
VFD
VFD.
what exactly is the circuit? Because that VFD box is available.
Then
We
they
are
have
connecting
to
our motor.
put
and we
one
are
more
putting
power
our
factor
wheels.
looming stage. So that will again increase the cost and further efficiency will decrease.
So see, in these applications, VFDs are not
Simply, this is the simplicity with economy.
So
What
better
specific
compare it with the stator voltage control. The second thing is that see, your analysis is slightly on the proper analysis. And the PhD is proper mathematical modeling and analysis. And you solve only one problem. See, that is only one problem.
Efficiency and power factor both here.
No, this topology is only one topology. So generally, from this point of view, at least two problems, two and a half problems are required. Anyway, so that depends on the expectation of your university. But the standard practice is that at least.
Sir, what's the problem is we are working in an environment where resources are restricted. And in that resources we will have to work hard and hard and
What
hard.
I'm saying is that what is the general practice?
Sir, for getting a single power analyzer, we will have to run here.
We have developed one for single phase also.
No, this is my general observation. How to interpret what the constraints you are facing, in these constraints, what you feel, and that you have to decide.
Depends
This is
on
altogether a
resources.
new
Depends on
topology. We are not
even sir,
existing topology.
we are planning to increase our work with the help of extinction angle. Same work
So
with
you
extinction angle.
don't have to do an experimental thing. You just propose, you can do a theoretical study. Theoretical study on that. That is also fine. You don't have to, you may work on three problems, but one problem, experimental results is sufficient. Two problems may go without experimental results. But the thing ultimately is, if you see the PhDs of other universities, at least there's only two problems. I'm not talking about the high-end integration. These two problems will be there. One with experimental results, one with the theoretical. Anyway, so it depends on what is the expectation of your university. And all the best. Thanks.
Even for this work, sir, sir has applied to patents.
Should the experiment
Okay, sir. Very good, sir.
for specific application, what I only want to say that we are necessarily using VFD where this type of drivers
That is well taken. That is well taken. But when you are actually comparing,
like we are not comparing for the complete range
Sir,
of
we are
VFD.
not comparing for
Or
each
very
and
small
every
range of
application.
application.
We are comparing for span purpose,
And that
for
is
pumps,
quite large in number in industry.
and for similar kinds of
also the
That
thing
is I
is,
will take this problem.
also the thing is that in stator voltage control device, you are losing efficiency or losing power due to high sleep operation as a switch is necessary. But then, in this case, there is a
The freewheeling thing is adding additional. It is not there in any case.
but in freewheeling energy, you are not getting it back. If you could
Then
get back,
we are getting energy circulated in the state dynamic itself. Because when the switches are off, the current is circulated in the same direction in the stator.
Right. So that will be substantial. That it is taking part in the torque production.
That is the thing which we are not taking.
Right.
Very small time it is charging the capacitor, but most of the time it is free.
So that freewheeling energy, but you are wasting that energy. No, by turning on that switch, the capacitor voltage.
A very small amount of
So you have to substantiate that energy is actually being used for torque production.
Sir, that time is intentionally given in order to
that is controllable
avoid
that time. We can almost
short circuit between the
and if we use head bridge,
even if
then that can be avoided. If we are using induction,
that is okay. The only thing is actually this energy which you are saying that during freewheeling, that current is also helping you out in torque production. So that is substantial to analysis. That will improve the efficacy of your product.
that can be done, sir. That can be done if we keep the dead band almost zero. And during dead band, we are doing inductance that will be limiting the
Yes.
in that case, that energy can not be wasted.
No, some analysis on that point. Because we are saying that your efficiency is improving. How it is improving? Because your sleep is increasing. So that has to be
so
substantial.
actually I am not saying with experimental results I come to that
Freewheeling is the thing.
Just with experiment you can't substantiate a problem. It has to be supported by analysis. An experiment that your magnetizing current, when you are comparing it, magnetizing current is very high. Your stator current is
That can help you in this.
comparable. Your stator current is comparable to the magnetizing current. So that's why it is actually pumping in. Anyway. Okay, others.
Okay.
Any query from the students? Okay. On behalf of the institute, I am extremely thankful to Professor Chatterjee for accepting our invitation and for being here for conduct of this presubmission seminar. And I am very sure that the PhD scholar will incorporate all the points in the work and the PhD thesis as a whole so as to improve the overall quality of the research. Thank you, Vandana.
Thank you all for your patience hearing. Thank you, sir. Thank you very much.
Yeah.